Good afternoon. Welcome to EduSat Network. Friend, we have organized two lectures on quantum chemistry. Today we'll have a kind of introductory lecture, and it is a difficult subject. We will just try to make it simplify it and make it to understand what exactly the quantum chemistry is. I know the application of quantum chemistry has increased in last, if you say last 2 decades, because the number of students are now taking interest and the applicability in different other fields have increased. So we'll try to understand just how introductory sort of thing, what exactly quantum chemistry is, how a student should study it. And for discussion on the topic, we have in studio Dr. Rita Kakkar. She is a professor of chemistry in Delhi University, and she has long experience, about more than 30 years of teaching experience, and her area of specialization is quantum chemistry. So on your behalf, I welcome her for EduSat lecture on this very topic. Welcome, ma'am.
Thank you. Hello viewers. Today, I'm going to give the introductory lecture on quantum chemistry. As you know, in recent years, the number of applications of quantum chemistry has increased. People are taking more interest in understanding quantum chemistry, but it is generally perceived as a very difficult subject, although it has so many applications. So there are many people who would like to learn more about it. The key is to understanding is to simplify it. You should not think of it as a mathematical subject, but instead of concentrating on the maths, we will try to concentrate on the conceptual topics. Here I've shown a lot of applications, but the number of applications is increasing every day. Today, with the birth of nanoscience, not birth exactly, but more applications of nanoscience, it has gained more importance, and that is why one needs to understand. If you think quantum chemistry is difficult, do not get worried, because even the people who introduced us to quantum chemistry, people like Bohr, who gave the first quantum mechanical atom, or Schrödinger, credited with the Schrödinger equation, or Feynman, the father of nanoscience, all of them thought that quantum was difficult. They did not believe in quantum, but they were forced to believe in it because there was overwhelming evidence that you had to understand quantum to understand the nature of matter. So here we'll see. Again, we are in the same boat as all of these people, Bohr and Feynman, because all of them did not understand quantum, did not appreciate quantum, but they were forced to do it because they had to understand it. Now, in today's lecture, I am going to talk about the birth of quantum chemistry, because it is very important to understand why people were forced to abandon Newton mechanics and go to quantum, which is much more difficult. The reason was that there were some baffling evidences from science which they were not able to explain with the classical theory. By classical theory, I mean theory given by people like Newton and other people at that time. This did not fit into the scheme of things. They were not able to explain the nature of electromagnetic radiation. Now, as you know, so the starting point is electromagnetic radiation, because the points that were not understood were all related to this. Spectroscopy is entirely due to electromagnetic radiation, so the starting point of any quantum mechanics study should be the electromagnetic radiation. Now, people at that time in the 19th century firmly believed that electromagnetic radiation consisted of waves, because there was a lot of information to this, a lot of evidence that proved diffraction, interference, superposition, all of these are characteristics of waves. The people were able to correlate all these properties like diffraction with the nature of electromagnetic radiation as a wave. Now, how do we define a wave? A wave is like a sine curve. It can be explained as sine theta. And according to Maxwell's equations, the light that they know of consists of is called electromagnetic radiation, because it has perpendicular electrical fields and magnetic fields, and it is a transverse wave. What do we mean by a transverse wave? A wave in which the oscillation is perpendicular to the direction the wave is propagating. If it is propagating in the z direction, then the electric field vector and the magnetic field vector, both of them will be in the x and y directions, perpendicular to the direction of propagation. So here I have shown blue lines to show the electric field vector and the magnetic vector as the reddish lines, and these are perpendicular to each other. All the vectors, electric vectors, are in one direction. Such a beam is said to be polarized because all the electric vectors are in one direction. Similarly, all the magnetic vectors are in another direction, perpendicular to the electric vector and perpendicular to the direction of propagation of the wave. A wave is also characterized by its wavelength. Now, since it is a sine curve, it goes through a maximum and a minimum, and between these there is a point of 0. If you characterize the maxima, which are called the crests of the wave, and take the distance between the two crests of adjoining waves, then we say that this is the wavelength, and this pattern is repeated throughout. Then we are also describing it as a transverse wave. Like I said, in transverse wave, the medium moves in the perpendicular direction to the propagation of wave, like the water waves. The waves keep on going up and down perpendicular to the direction of movement of the wave. Another quantity that is defined is the amplitude. That is the maximum distance that is traversed by the electric vector or the magnetic vector, both of which are the same. So this is how the waves were characterized, and it was Maxwell who first talked about electromagnetic waves, because he is the one who was able to correlate optics with electric and magnetic field character of waves. Now, another quantity that we must understand is that wavelength alone does not characterize an electromagnetic radiation. There is also another quantity called the frequency. The frequency is the number of cycles. As we said that once one cycle is completed, one wavelength is completed. The number of cycles per second is called the frequency of the wave, and it has the units of second inverse. Obviously, the wavelength is the amount of time travelled in a second, and the number of cycles per second is nu. Obviously, this is equal to the product of these two is equal to the speed of light. Now, it is not any speed. It is not the speed of a ball or anything. It is a special name given to this, and it is called c. It is the speed of light. Nothing can exceed the speed of light, and this is what was proposed by Einstein, that the speed of light is so large, 3 into 10 raised power of 8 meters per second, that you cannot exceed the speed, nothing can exceed the speed, and that is why we are not able to go to distant planets, because it is not possible for us to complete a journey in a lifetime, although the speed is so large. Now, it is not just one wavelength. The earliest people were aware of visible light. They were able to see the colors, and they knew that it was visible light, had all these colors starting from the violet up to the red colors. But later studies showed that to the less frequency side of red radiation, there is also another kind of radiation which is infrared, and heat is associated with it. The temperature is associated with the infrared radiation, and beyond the violet there is a higher energy radiation which is now called ultraviolet, and that is due to it is coming from the sun, and this is what causes harm. It has a lot of energy, and it causes, among other things, electronic transitions. A property of wave that they were aware of was interference. What we mean by that is, if there are two waves and they are incident at the same spot, then the sum of these waves will give you the final wave. That means if their troughs and their crests are incident at the same point, the net amplitude will become double if both waves have the same amplitude, and in case the trough of one wave is meeting the crest of another wave, in that case it will be the wave will just disappear. It will be destructive interference. The first is called constructive interference, where the waves are becoming larger, they are contributing to each other, and the other one is destructive interference, where they are just destroying each other. Now, if you go to history, the first time that anyone talked about something called quantization was Max Planck, and this was around 1901, and he got the Nobel Prize in 1932 for this. He was not convinced about quantization, but like he said, for 6 years he struggled with himself whether to propose this theory or not, but he was forced to do that because there was something about black body radiation that was not explained by the conventional theory, Newton mechanics and so on. Then it is the photoelectric effect by Einstein, that also Einstein had to extend whatever they knew about electromagnetic radiation to Planck's theory, and he said that electromagnetic radiation itself consisted of photons, particles, which had energies which were fixed and proportional to the Planck's constant multiplied by the frequency. And then finally Bohr gave the hydrogen atom. So there were so many observations that were not explained by the theory at that time. Scientists at that time believed that they had discovered everything they needed to know, but there were some things that they were inexplicable. The first thing is, now the first evidence that came from black body radiation. What is a black body? A black body is an object that absorbs all incident radiation and it also emits it. That means there is no reflection. It absorbs all the radiation that is incident on it, and it can also emit it. Now, what was the problem with the black body? How do we show what a black body looks like? Suppose it is a cavity in something which has a very small hole. All the radiation that comes in will suffer multiple reflections inside the cavity and then come out once it is near the hole there. So we are showing a small cut in a cavity, and this is one of the most popular and realistic examples of a black body. Now what happens to this radiation? This radiation is absorbed by the walls of the cavity. It is in equilibrium with the walls of the cavity, and what happens? The cavity walls start heating up. The material of the cavity, the atoms inside the cavity, they will start oscillating faster, and there is a characteristic frequency with which they will start oscillating, and after this they will start re-radiating the energy and there will be a new characteristic frequency. Now what was wrong with the theories at that time? The emitted thermal radiation characterizes the equilibrium temperature of the black body. So this is these are what people knew about black body radiation, that the maximum value of lambda that was observed from the emitted radiation was proportional to 1 by T, the temperature, and this was Wien's law given in 1893. And at 300 K we are also radiating. At 300 K we are radiating in the infrared. That is why there is no visible radiation, but every body radiates. Objects at 600 to 700, when you heat something, you must have observed that you heat, say, a tawa, what happens? At some temperature it starts to glow, it starts glowing red, and then after some time it starts emitting white light. What is happening? From red, which is the lowest energy end of the visible spectrum, it goes over to blue, and then all the colors are emitted because white light is a mixture of all the colors, and when it becomes even higher, then you are not able to see, it starts emitting UV radiation also. But now this Wien's law had been long used. In the 19th century it had been proposed, and it was used to find out the temperature of the stars, and this whole held good for some wavelengths, but there were some problems. Now if you plot the wavelength and intensity of black body radiation, what is observed is that this constant relation does not hold everywhere. If you plot the intensity versus the wavelength, there is a maximum, and the maximum shifts as you increase the temperature from 1300 K to 2000 K. You see the maximum is shifting to shorter wavelengths. Remember that lambda into nu is equal to the speed. So since both of them are constant, if the frequency is larger, then the energy of the radiation is larger, and that means that the wavelength is smaller. That means when you raise the temperature of your black body, the temperature at which the maximum, the wavelength at which the maximum intensity is observed shifts to smaller wavelengths, that means higher energies, higher frequencies. Now at that time, according to the wave nature, this is what they thought, that Rayleigh and Jeans, two scientists of that time, they gave Rayleigh-Jeans law. They said that we've already seen that waves interfere with each other. That means that if a wave is traveling in one direction and then it returns, then there will again be an interference with each other. Electromagnetic radiation consists of traveling waves. They are traveling in one direction. When they hit the wall of the cavity, they return. Now, when they reflect, a trough becomes a crest, and a crest becomes a trough. They are reflected opposite to each other. That means unless at the cavity wall there is no amplitude, the wave has no displacement at the node, when it returns there will be destructive interference and the wave will disappear and you will not see emission. The only wavelengths that will be observed will be those which go to the wall and there is something called a node where there is no displacement, that is a node, and if they meet a node there, then when they return there will be constructive interference and this wave will be reflected back. But if at the walls there is no node is where the displacement is zero, in that case that wave will not survive. What does it mean? That shorter waves have more chances of finding a node at the wall than longer wavelengths, and we would expect that most of the waves would be emitted with lower frequency rather than higher frequency. Lower wavelengths rather than higher wavelength. And this means that if you sit before a fire, what you would see is a very high energy radiation coming, and that is like gamma radiation or very high energy radiation will be coming. But at the lower end, the microwave and infrared region, we will not see any emission in this in front of a fire. But what is actually observed is that you feel heat in front of the fire. That means more of infrared radiation is being emitted. This was against what the classical theory at that time, the classical wave picture had predicted, that only those wavelengths which were shorter, that means higher frequency, which were in the higher energy ultraviolet region and so on, they would be emitted. Now, where were they wrong? According to the Rayleigh-Jeans law, the frequency was the intensity would be proportional to the square of the frequency. That means larger the frequencies, larger will be the radiation. In the graph on the right, what you see is the Rayleigh-Jeans law, which says that the shorter wavelengths have a larger chance of being there. There was another theorem at that time, which was the equipartition theorem, which said that every node that they called, every wavelength that survived would get an equal proportion of the total energy. Since there are more nodes with lower wavelengths, that is higher energy and higher frequency, one would expect that all the energy of electromagnetic radiation would be collected in the lower wavelengths, and as I said that before a fire you would experience ultraviolet radiation, which is very harmful. We protect ourselves from the sun's ultraviolet radiation because we know it causes a number of diseases like cancer, skin cancer and so on. So, but we comfortably sit before the fire without getting this kind of radiation, and so there was something wrong with this theorem. Quantum theory predicts something else, that there is you see in the denominator on the right hand side of the second row, that there is something in the denominator, and this equation was first derived by Planck. What Planck said was that there is a quantization of energy levels of the oscillators. They cannot have all energies. The energies are fixed, and each oscillator can either have an energy of h nu or 2h nu or 3h nu and so on. It cannot have any energy like say half h nu. It could be either 0 or h nu or 2h nu. There was something wrong in this derivation. We now know that there is a 0 point energy. The minimum energy the oscillator can have is half h nu, and the next one is 3 by 2 h nu. But the point is this, that between one energy level and the other, there was no oscillator with that energy. This means that if an oscillator emitted radiation, if it got into an excited state, it could only emit radiation corresponding to the difference between two energy levels, nothing in between. What does this mean? This means that the higher energy oscillators, they also knew about Boltzmann distribution law. According to Boltzmann's distribution law, which I have written at the bottom, the probability that an oscillator has a particular energy depends upon the exponential of minus E, that energy, divided by Boltzmann constant into the temperature. The higher the energy, because you have a negative sign in the exponential, the higher the energy, the probability is less. This explained that the higher energy radiation would not be emitted so much, because there would be very few oscillators with higher energy, and hence Planck was able to explain the black body radiation. What he explained was that even though there will be more wavelengths with lower wavelengths, there would be more modes with lower wavelengths, their probability would decrease, because there would be very few oscillators which would be oscillating with that wavelength. Then this was done in 1901, and as I said, he got the Nobel Prize years later in 1932 for this discovery. Meanwhile, in 1905, Einstein tried to explain the photoelectric effect. Photoelectric effect was first observed in 1886 or 1887 by Hertz. I showed you the regions of the electromagnetic radiation. They start from the lowest energy radio frequency region to the highest energy cosmic rays, which are somewhere in the high atmospheres. The lowest energy region is the radio frequency region, and this was first discovered by Hertz. Hertz is the person, if you observe the frequencies of all the radiations in the radio waves, the FM channels, they say that the frequency is so many hertz. Hertz is the unit of frequency, which means second inverse, and this is named after Hertz, the scientist who first discovered them. He discovered them in 1896 or 1886 or 1887, and he built the world's first radio at that time. How did he prepare this radio? He wanted to see what happens to transmit radiation, and because electromagnetic radiation does not need a medium, he tried to transmit. He made a receiver and he tried to transmit a spark to that receiver using his radio that he had, crude radio that he had built. What he observed was that if some radiation was shined on the metal balls that he took polished brass knobs, then the reception became better. Now, at that time, they did not even know about the electrons. The electrons were discovered much later by Thomson, and later on they got to know that this radiation that was shined on the metal or illuminated on the metal, this caused the electrons to be emitted. Now, this was not very surprising, because if they believed that metals consisted of sea of electrons floating around the surface of the metal, so if you apply an electromagnetic radiation, you expect that it will push out the electrons and they will go away. So this was not very discovering. What was difficult to understand by the scientists of that time was the influence of frequency and the intensity on the radiation that was emitted by these, the photoelectric effect. Einstein thought about Planck's discovery, and what he thought was that if the oscillators and if the radiation has quantized energy levels, so why should it not consist of particles which have some quantized energy levels? And he used Planck's constant, and he was able to explain. Now, what were the problems that they were facing they were not able to understand? If the radiation consists of waves, according to the particles are oscillating, then using the simple harmonic oscillator model, one can show that the energy of a wave is proportional to the square of the amplitude. This means that the intensity of a beam of radiation depends upon the amplitude square. Now, what was difficult to understand was that when they increased the intensity of the radiation, even then for some metals they were not able to see any emission of electrons. But even the lowest energy radiation that they took of higher frequency was able to affect that change. It is like something, if you have lots of boats on the ocean, and a small wave is able to knock off the boat, but a high wave is not able to do it. Now, what was it that was going wrong. If they used red radiation, no emission of electrons. They were measuring using ammeter device the amount of current that was being observed, but they found that red light was not able to cause any change, but blue light was able to do. And this one, that higher frequency of blue light was able to emit electrons, but the lower frequency red light was not able to do. Even low intensities of blue light was able to cause the electrons to be emitted, but low intensity of or high intensity of red light was not able to do the job. So the important thing was the frequency and not the amplitude or the intensity that they were talking about. Another thing that they thought was there would be a time lag as the electrons, the oscillators or whatever, they would be getting energy from the electromagnetic radiation. As they would gain more and more energy, they would start oscillating faster and the electrons would then be emitted. But this was not the case. If they had the correct frequency, even one electron would be knocked off, and if the intensity increased, more electrons were knocked off, but provided they had the right frequency. It is like you have a lot of boats in the harbor, and a wave is able to knock off one electron, one boat out of the entire collection of boats, instead of distributing the energy equally to all the boats. So at that time, if you think like classical mechanics, it is very difficult to understand this. The moment Einstein entered the picture, he described this, that the light consists of photons, particles which have a specific energy, and each photon has an energy equal to h nu, and that is why the energy depends upon the frequency of the radiation and not on the intensity. One photon is able to knock off one electron, and that is why if you increase the intensity, there are more photons, and we find that the intensity of the emitted electrons, the amount of current that is observed, keeps on increasing. So all the problems that were associated with the photoelectric effect were removed by this one thing that Einstein proposed, that the energy of a photon is proportional to the frequency and it is equal to h nu. Now, what else were the problems that were associated? All these people were not really convinced about what they were saying, but they had to. Now, what were the observations of the photoelectric effect? Only light with a frequency greater than a certain threshold produces a current. Now we know that this threshold is dependent upon the kind of material that is present. And suppose you have an alkali metal, it is easier to remove an electron from an alkali metal. You know that it has only one electron in its outermost S shell, and so it is very easy to remove that electron. But if you take something which has more, it is more difficult to remove that electron, then the threshold will be greater. This threshold is related to the ionization energy of the material. So it depends upon the material. But once that threshold was crossed, after that there was no problem. You could easily knock off the electrons. Now we know that you don't need only visible radiation. For some metals for which it is difficult to remove the electrons, you may need ultraviolet radiation, or some metals, or mainly semiconductors, they have very low ionization energies, and with those even infrared radiation is able to knock off the electrons. But at that time they were only aware about the visible radiation. What else was observed? That current begins almost instantaneously. What they thought was that as you keep on shining radiation on it, as the intensity increases, slowly it keeps on absorbing the energy until it has enough energy to get removed from the material, the electron has enough energy to escape. Now what was observed is, as soon as the radiation was shined on it, the electrons started getting emitted, a current was observed, and this was against what they had thought according to classical theory. Again, they found that the current is proportional to the intensity of the incident light. When you increase the intensity, the number of photons increases, and that is why the number of electrons that is knocked off increases, and so the current also increases. So Einstein's explanation was absolutely correct, and you see that the intensity according to classical physics was proportional to the amplitude square, which is actually the amplitude of the electric field square. As the intensity of the light increases, the electrons on the surface of the metal should oscillate more vigorously. At some point, the electrons will have sufficient energy to escape the metal. Frequency was not important in that picture. It was only that if you kept on increasing the intensity, then the energy would keep on increasing, and at some point when it had enough energy, there would be a time lag until when it got the enough energy to escape, then only it would escape. And what experiment showed was that there is a threshold frequency, and this threshold frequency and a threshold intensity also that caused the electrons to be removed, and there was a straight line. And for different materials, they got straight lines which had the same slope, but the threshold frequency was different, so they got different parallel lines depending upon the intensity, upon the ionization energy of the material. Now, since the slope is the same and this slope is equal to Planck's constant, Einstein's theory was verified. The maximum kinetic energy of ejected electrons versus the light frequency on the sodium plate you see is a straight line, and the light shines on a chunk of alkali metal. Alkali metals have the lowest ionization energies. So you find this. Now, how did Einstein explain these phenomena? He said that these quanta of light, these are quanta. Quanta is a small particle. They are they have an energy equal to h nu, so that the kinetic energy of the, once you have the correct frequency, the minimum frequency required, if you add more frequency, the extra energy goes into the kinetic energy of the electron that is emitted. Part of the kinetic part of the frequency, the energy of the radiation is used to emit the electron, and this is to overcome the ionization energy. The extra energy that you provide can be continuously absorbed, and this goes into the kinetic energy, so that we can say that the kinetic energy of the emitted electrons will be equal to half mv square, and that means the velocity will depend upon the kinetic energy, and it is equal to h2 of the radiation. Frequency of the radiation is very important, minus phi, which was called the work function, and h2 naught is equal to phi, because this is the minimum energy. It is the threshold frequency mu naught which is required to emit the photon. Any extra energy goes into increasing the kinetic energy of the photons. Einstein proposed that electromagnetic radiation itself is quantized, and just as Planck had previously postulated that energy levels in a black body oscillator are quantized. Now, another puzzling phenomenon was the hydrogen atom spectrum. Suppose you heat up an atom, then we now know that they go into higher energy levels, and they start emitting light when they come down to the ground state, because the higher energy states are not stable. Now, one would have expected that light of any frequency would be emitted once it tries to come down to the ground state, but this was not observed. If you look at the black film, you see that there are regions where there are lines, and these lines depend upon the element that you have taken. Whether you've taken hydrogen or you've taken any other element, you will get a different kind of lines that are observed. That means that the radiation is emitted. It is not emitted continuously. It is emitted as discrete packets of energy called quanta. Quanta is a packet of energy. Bohr had observed one series of such lines. He was mathematically, remember that Planck also, for him it was a mathematical necessity to get an equation that fit into that black body radiation maxima. It was only mathematical. They were not able to explain why it happens, and it is now that our understanding has increased that we are able to explain. For Einstein, he took his mathematical necessity, as he called it, and then he was able to understand the picture. So now we know that the electromagnetic radiation consists of waves. It also can behave like packets of energy called photons. Bohr observed that the line spectrum of atoms could not be explained by classical physics, because classical physics did not say anything about quanta of radiation. That means the radiation would be emitted continuously. You would not get spectrum. In fact, spectroscopy is based on quantization. If there were no quantization, there would be no spectra at all. what they observed was Balmer series was observed in the visible region, and he found that just mathematically he was able to fit what is called this nu bar that I have used is a symbol that we use for wave number. How many waves are contained in 1 centimeter in, for example, and obviously the unit would be centimeter inverse. And he found that there was a constant 109680, and he could fit all his lines into an equation where 1 by 2 square minus 1 by n square, 2 square was constant but n could vary. It could be any number greater than 2, it could be 3, 4, 5, but it had to be an integer, it had to be a whole number. And nu bar could be given as it is equal to 1 by lambda, because I said it is the number of waves that is contained in 1 centimeter, and if lambda is given in centimeter, the SI units for wavelength or for anything are any length is meter, but we continue using other units. In fact, nanometer is the best unit to use for lambda, and for nu bar we should be using meter inverse, but it is only a convenience, and historically centimeter inverse was being used, so we continue using centimeter inverse. And in terms of wave number, he was able to write something like RH 1 by n1 square minus 1 by n2 square. N2 had to be greater than n1. In his case, n1 was equal to 2 and n2 could be 3, 4, 5, anything. This constant that was observed is called Rydberg's constant, and it has a value equal to 109677.57 in centimeter inverse. This is actually not a very accurate value, because it is for an electron and nucleus at infinite distance. They are not at infinite distance, they are bound to each other, so there is a slight difference. For example, for deuterium the value would be different. The line spectrum of atoms could not be explained by classical physics. It required a quantum hypothesis. Anytime you talk about discrete energy levels, you are talking about quantization. So quantization had to be introduced, and this was the first hydrogen atom emission series that was observed by Balmer, and this was observed in the visible region because at that time they did not have so many instruments for the other regions which were invisible. Bohr tried to explain this, and probably he is considered because he gave us the beginning of the understanding of atomic structure, and it is Niels Bohr, and he is the foremost. All of the people that I am talking about, they earn Nobel prizes for their startling actually discoveries, because till that time nobody even thought of quantization. Today we accept it, and we have lots of applications, particularly since nanomaterials have come into the picture, and they are small, they are in the region between quantization and between the classical picture, and so they display interesting phenomena. Niels Bohr, he was the first to apply Planck's quantum idea to problems in atomic physics. In the early 1900s, Bohr proposed a quantum mechanical description of the atom to replace the early model of Rutherford. Rutherford, if you remember, was also trying to discover the structure of atoms. He used the gold foil experiment, which was so thin, he pounded it to such a thin sheet that was only as thick as one atom, and then he used alpha particles. At that time they were known, although they did not know that they were helium nuclei, and he bombarded them through the gold foil. And the surprising discovery was that most of them just passed through. That means that most of the region in space between the atom, between the electron and the nucleus, he said, is free space. But some of them were reflected back, and reflected back so much that some of them just returned. And this meant that there was something very, very positive, because the alpha particles were positively charged, which was repelling these alpha particles so much that they were returning. And his model was that there is a sea of electrons surrounding the nuclei. There are nuclei which contain all the positive charge, and the electrons are just around the nucleus. Now the problem with his model was that if the electrons are rotating outside the nucleus, they will be losing energy, because classically it is known that if a rotating particle, that means it is constantly changing its acceleration, it will be emitting radiation, and it will be losing energy, and finally it will fall into the nucleus. Then how was this explained? This was the problem with the Rutherford model, that if you have a particle which is charged and it is moving in space and it is moving with constant acceleration, what the speed is going on changing because it is moving in a circle. What was predicted by the earlier models was that it would keep on emitting radiation. If it emits radiation, its energy keeps on decreasing. That means it will be moving in smaller and smaller cycles until in a spiral form it will fall into the nucleus. So finally we would expect, what Bohr said was that this is not true if the electron is moving in certain orbits. He was not able to explain why these orbits were the ones that were allowed, but if it was moving in these orbits, then electromagnetic radiation would not be emitted. It would be a stable electron. It would be moving around the nucleus in distinctive orbits. It would not fall into it, and there were different orbits corresponding to n is equal to 1, which was closest in energy, n is equal to 2, closest to the nucleus was n is equal to 1, n is equal to 2 was further away from the nucleus, n is equal to 3 was still further, and so on. And the n is equal to 1 had the lowest energy, I mean the most negative energy, because it was closest to the nucleus and it felt the attraction to the positive charge on the nucleus. And these n quantum numbers were the same that were observed by Bohr. So he tried to relate whatever they had known about from the structure of the atom from the Bohr series, and he said there is a quantum number which is now called the principal quantum number. He said if absorption of radiation takes place, then an electron in an n is equal to 1 orbit goes to the n is equal to 2 level, and if emission takes place, for example n is equal to 3 would fall to n is equal to 2, and since it is losing energy there would be emission of radiation. And here we have shown the stepwise energy levels. You find that the lowest one is minus 13.4, we know 13.6 electron volts we know now. The n is equal to 2 is 1/4 of that, n is equal to 3 is 1/9 of that, and so on, 1/16, n is equal to 4, and as the distance from the nucleus is going on increasing, the energy is going on getting higher and higher towards 0. 0 is the energy when both of the electron and the nucleus are at infinite distance from each other. So the electron travels in a circular orbit around the nucleus. The orbits are quantized, and the radius of these orbits is also quantized according to Bohr model, that it can have only certain radii, but once in those radii the electron is stable, it does not emit radiation. It cannot be between the, for example, 2 and 3 levels, it has to be either in 2 or in 3, and it can move between these levels by absorption or emission of radiation, and the wavelengths are can be calculated, because we know that delta E is equal to h nu and nu is equal to c by lambda. We have already seen that, so we can calculate. So this is how we would picture the atomic spectra. Before spectrum, when the electron is in an excited state, then it can according to the Bohr atom, it had energy levels 1, 2, 3, 4 and so on. It would go by absorption to a higher energy level, and then it or emit to a lower energy level, and that means that the wavelength that is emitted or absorbed can be calculated from Bohr's theory, because they already knew the Rydberg constant. One of the postulates of Bohr was not only about the orbits. He said these orbits are governed by something called the quantization of angular momentum. Angular momentum in quantum mechanics is generally given the symbol L. The magnitude according to classical mechanics is mdr, where b is the velocity and r is the radius of motion and n is the mass of the particle. According to Planck, that this mdr, the the angular momentum could not take on any value. It had to take values which were integral multiples of h cross. H cross means h divided by 2 pi. So it was equal to n multiplied by h divided by 2 pi, where pi is the normal pi that we use, and this is where I have shown the angular momentum classically is given by the cross product of r into the linear momentum, and this is how we visualize it. Meanwhile, de Broglie had suggested that if waves can behave, the light can behave as waves, then why not matter can also behave like waves. Light can behave as both as a particle and as a wave. So even matter could behave both as particle, as we know of, and it could also behave like a wave. So every particle will have a wave characteristic as well as a particle characteristic. The wave characteristic is something we are not aware of, be associated with light and electromagnetic radiation, but every matter has some wave characteristic. The only difference is that according to the de Broglie equation, it is lambda is equal to the wavelength of any matter is equal to h by md. Since most of the matter we are concerned with is m, has a large value of m, that means lambda is very small and we are not able to measure it.
Sorry to interrupt you, ma'am. We have a call from Bihar, so first we take the question. Good afternoon, friends. Please ask your question. Yeah, go ahead. Please ask your question.
यदि किसी तत्व की परमाणु संख्या 1.5 है, तो क्या आवर्त सारणी में से हाइड्रोजन और हीलियम के बीच रखा जा सकता है?
जी, फिर से सवाल पूछिए।
यदि तत्व की परमाणु संख्या 1.5 है, तो आवर्त सारणी में हाइड्रोजन के बीच रखा जा सकता है?
There is echo sound. Please reduce the volume of your television, then ask your question. Yeah.
आवाज नहीं आ रहा।
फिर से सवाल पूछिए।
यदि किसी तत्व की परमाणु संख्या 1.5 है, क्या आवर्त सारणी में हाइड्रोजन और हीलियम के बीच रखा जा सकता है?
किसी का परमाणु संख्या 105 है तो हाइड्रोजन और हीलियम के बीच में रखा जा सकता है, इस तरह का सवाल है। किसके बारे में बता रहे हैं? ओके, टेक्स्ट में मैसेज भी आ सकता है, टेक्स्ट मैसेज में। ओके, मैं कंटिन्यू।
So according to him, that is why we are also radiating, but our radiation is in the infrared that we cannot observe. That is why we are giving off heat. Okay, now he was the first one who introduced the quantized orbits, Bohr's theory. If you complement it with what de Broglie had said, you can see that if you are able to fit on the circumference a wave an integral number of times, there won't be any interference. And if you look on the right hand side, we have derived an equation. If on the circumference you have an integral number of waves, 2 pi r is the circumference of a circle, and this is equal to n lambda, where n is a whole number. That means lambda is equal to h by p. If I substitute, I get nh by mv, and or mvr, which is what I said is the angular momentum, is equal to nh 2 pi, and that means it is equal to nh cross, exactly what Bohr had postulated without looking at the interference pattern. So if you look at the n is equal to 4 orbit, there are 4 wavelengths that are fitting in. If n is equal to 6, there will be smaller wavelengths, higher energy, and there will be 6 wavelengths that will be fitting in. So this makes a very elegant way of explaining quantized orbits, and you have a number of them. So if you look at the de Broglie wavelengths, if you have a particle like say photon, yellow radiation has a wavelength of around 600 nanometers, visible radiation has wavelength between 400 nanometers to around 780 nanometers, 600 comes somewhere in between and it is yellow. An electron, if you put in the value of the mass and the velocity with which the electron, suppose it is moving with a velocity of 10 raised to the power of 5 meters per second, in that case we will find that its wavelength is 6. Sodium at 80 Kelvin temperature with a velocity of 300 meter per second has a wavelength of around 0.06 nanometer, and a base ball of 170 grams with a velocity of 40 meters per second has a wavelength so small. That means it is so small that the number of waves that is contained in 1 centimeter is very large. It is almost as if it is a continuous distribution. The time period of a wave is the reciprocal of the frequency. It is so large that it will take years to see the entire wave. So now we have wave particle duality. We have shown that that quantities such as waves, which were traditionally thought of as waves, had photon character, and so they had both particle and wave character. Similarly, it was shown that the particles also had wave character, and this was very elegantly shown by de Broglie. The scientists of that time did not have so many instruments, so they were actually doing thought experiments. De Broglie proposed this during his PhD work, and during his viva voce examination he asked, how do you prove what you are saying, that matter also has waves? He said electrons may have the correct wavelength so that you will be able to see a diffraction, and a crystal of sodium chloride, for example, will show a diffraction pattern. And Stern and Rayleigh, you remember the persons who discovered spin also, they promptly performed an experiment, and they were able to show that they were able to get in a picture of electron diffraction, and just like the X-ray gives a diffraction pattern, you see that electron also gives a diffraction pattern. And till probably till school level you thought that electrons were particles and X-rays were waves. Now we know that both have similar characteristics, they show similar. And combining the wave equation with the particle character, Schrödinger was able to give his Schrödinger wave equation, where he combined the two. Classical physics said that the total Hamiltonian is equal to the kinetic energy, which we normally use the T.
We have another call from Bihar. We'll take up the question. Good afternoon, friend. Can you ask your question?
कैसे प्राप्त यूरेनियम के बाद सभी तंत्र कैसे प्राप्त किए जाते हैं?
यूरेनियम का
बाद वाले तंत्र प्राप्त किए जाते हैं,
तो उनको नंबर दे दीजिए, उनसे टेक्स्ट मैसेज में।
यूरेनियम के बाद वाले तंत्र, यूरेनियम के परमाणु तंत्र के बाद वाले तंत्र कैसे प्राप्त?
So Schrödinger was the first one who combined both the things. He said classical mechanics told us that the total energy is conserved. By that we mean that the total energy does not change. It is equal to the kinetic energy plus the potential energy, and we can call it E. And according to the Schrödinger equation, that there is something called a Hamiltonian. It is an operator, and this is equal to minus iota h cross d psi by dt. This is the operator corresponding to the energy. He is able to get it, and this is equal to minus h cross square by 2m del square. Del square is the Laplacian operator, and plus the potential energy, and this is the potential energy term which varies with what system you are looking at, and it contains both wave and particle terms. How does it contain the particle terms? It contains a mass, so it has a particle term there, and it cannot be derived from any other principle since it constitutes a fundamental law of nature. The proof of Schrödinger's equation is that nobody has proved it wrong. It is just proposed. It is an empirical equation that was proposed, and it is a fundamental law of nature. It is applicable to everything, and its correctness can be judged only by its subsequent agreement with observed phenomena. That is, it is no proof is present, but you can say that it is correct. Now the classical wave equation, starting, one can give an argument in favor of Schrödinger's equation. What must have been his thought process when he gave this equation? The classical wave equation is given as del square psi, the psi is the wave function of the wave, minus 1 by c square, the speed, if it has a speed of light, is d2 psi by dx square is equal to 0. The del square operator is also called the Laplacian operator. Del square is equal to d2 by dx square plus d2 by dy square plus d2 by dz square, because everything is three-dimensional. Wave motion, if it is propagating in the x direction, will have an equation which is like this: exponential 2 pi iota. Iota is an imaginary number. See, the wave function can be imaginary. It is an imaginary number corresponding to square root of -1. Since the wave is also traveling in the x direction you have an x by lambda, it is also moving with time, so there is a time value also there. So it is 2 pi iota x by lambda, the number of wavelengths contained, minus mu, the frequency, and the time at which you are observing the wave. When you apply the Planck and de Broglie's formula to this, you get this equation. Exponential, you can write down, this is 2 pi x by lambda, we have substituted by the momentum into x, minus Et, the energy and time, because the frequency 2 pi mu into h is equal to the frequency, the whole thing divided by h cross, where h cross is equal to h by 2 pi. You get the one dimensional Schrödinger equation by just substituting this formula, E is equal to half mv square and so on, and you finally have this equation which is called the Schrödinger equation. This is not the familiar form of the Schrödinger equation, but we can prove that this actually becomes h psi is equal to E psi when you are so these are waves in 3 dimensions, and for a conservative system, one can show that this time dependence can be written as an exponential function minus iota Et by h cross, and later on we will show that it really does not matter whatever the time dependent function is. The stationary state for conservative systems are those for which the energy is fixed. For them, the Schrödinger wave equation becomes minus h cross square by 2m del square plus the potential energy, which is different for different systems, and this is an operator, and this, when it operates on a wave function, gives you the energy multiplied by the wave function. This energy has to be a constant because it does not depend upon the position, and if you can find a wave function that satisfies this equation, you have found everything about that particular system. Now we are talking about operators. The term that I have written within brackets is an operator. An operator is something that tells you what to do to the function. For example, square root is an operator. It tells you, if you write down square root of 9, it is 3, it tells you that 9 is the function, and what to do with the square root is to find out the square root. Square is again an operator. Anything differential is an operator. It is a generalization of the concept of a function. Whereas a function is a rule for turning one number into another, an operator is a rule for turning one function into another. What is a function? For example, if I say it's a function x square and I want to find it at the value x is equal to 2, you will simply say that it is equal to 4. It tells you what to do with the function. The one function gets converted to another. An operator converts one function to another. Laplacian is one function, the del square operator that we showed is one such operator, and normally we indicate that this is a function and not a constant by putting a hat or a caret symbol over it. So A with a hat over it tells you that this is an operator and you have to operate. For example, dy dx with an operator symbol above it tells you that you have to differentiate the function that is after this. And these are some quantum mechanical operators. The ones that one needs to remember is that the px operator, the linear momentum in the x direction is minus iota, again that imaginary number corresponding to square root of minus 1. Then dy dx, similarly py will be dy dy and so on. The Hamiltonian is another operator, and any operator, for example A converts a function f into another function g. For a single particle system, the wave function for the time dependent case represents the amplitude of the matter waves. It is something related to the amplitude of the matter waves, and Max Born told us that the wave function has no meaning. It is what has meaning is its square. It represents the probability that something is in a particular volume element, and since it represents a probability, its square differentiated over all integrated over all space should be equal to 1. We normalize the wave function so that we have this, and our wave function should be well behaved. That means it should be single valued, finite, continuous.
1 minute. 1 minute.
1 minute. Okay, so what we said is when we write down the Schrödinger equation, there are two parts. There is an operator and there is also a wave function. The wave function on the operator operates on the wave function and gives you the wave function back again multiplied by a constant.
Okay, so well friends, this was the introductory lecture. Tomorrow we will have another lecture on quantum chemistry. So I thank all of you for watching the lecture, and on behalf I thank Dr. Rita Kapra for giving such a wonderful lecture on this topic. Thank you very much.